Today, we will talk about magnetic flux and Faraday's law of induction. Magnetic flux is similar to electric flux in that it deals with a field permeating an area. The magnetic flux is defined as the strength of the field times the area bound by the loop times the cosine of the angle between the normal to the loop and the field itself. Flux, thus, can change with the strength of the field, the area of the loop, and the angle made between the loop and the field. Maximum flux is attained when the loop and the field are perpendicular to each other. Faraday's law of induction tells us that a changing magnetic flux with respect to time will induce an EMF in a loop. Here, in this equation, N is the number of loops in the coil, so you can have multiple loops. Induction is usually achieved by changing the angle between the field and the loop, for example, by rotating the loop. In our first example, we have a cube with side length of 1/2 meter in a uniform magnetic field of strength 0.45 teslas. The field is diagonal to the front face of the cube. We would like to know what the magnetic flux is through each surface and through the entire cube. Since we know the side length of the cube, we can find the area of each of its 6 surfaces as being the side length squared, giving us 0.25 meters squared. With our areas, we can now calculate the flux through each of the surfaces. The magnetic field does not penetrate the front surface, it merely runs along it. Thus, cosine of 90 degrees being the angle between them, gives us an answer of 0 Webers. On the back surface, the same is the case. The field does not penetrate the surface. On the top side, we can draw a surface normal and then find the angle between the surface normal and the field lines to be 135 degrees. This gives us a flux of negative 0.08 Webers. For the bottom, we again draw a surface normal and find that we have 45 degrees between the field and the surface normal. This gives positive 0.08 Webers. For the right side, gives 45 degrees with 0.08 Webers. And the left side, we again have an angle of 135 degrees, yielding negative 0.08 Webers. For the whole cube, we sum up each of the individual fluxes and find that the net flux through the entire cube is 0 Webers. Gauss's law for magnetism states that the magnetic flux through any closed surface must be 0. In our second example, we have a 0.25 meter long coil with 560 square turns, with 6.5 centimeters being the side length measurement. The coil is suspended in a magnetic field of strength 1.2 teslas. The coil is oriented so that its axis coincides with the field direction, as shown in the diagram. Then it is rotated to be perpendicular to the field direction in 0.2 milliseconds. We would like to find the magnitude of the EMF induced in the coil. Before we rotate the coil, the angle made between the coil's loops and the magnetic field is 0 degrees. So, before rotation, the flux simplifies to simply the field times the area of one of the loops. After we rotate the coil, the angle made is 90 degrees, giving us a flux of 0 Webers, no matter what the field strength or area is. So we can say that the change in flux for one of the loops in the coil is the flux after the rotation minus the flux before the rotation. This is 0 minus B times A, or negative 1.2 teslas times 6.5 times 10 to the minus 2 square meters, giving us a final change in flux of negative 0.00507 Webers. Now, we can plug our numbers into Faraday's law, as we have 560 turns in the coil, negative 0.00507 Webers as the change in flux, and 0.2 milliseconds as the change in time. So, the total EMF induced in the coil is 1.4 times 10 to the 4th volts.